Okay guys, in this video we're going to start chapter 13. And this is on page 564. And again, I'm just following the syllabus. Now, the difficulty with this chapter is called Solutions. We're gonna learn it kind of superficially because some of the factors that make a solute, in the moment I will be defining the terms, dissolve in a solvent, has to do with the certain chapters that we skipped in here because they're not part of the syllabus. But I'll do my best to explain you guys those, I guess, physical properties that make one solute to be dissolved by the solvent, and vice versa. A solute Y does not dissolve in the particular solvent. Okay, so I'm going to start with page 564, and there's a definition of solution, and in my opinion, that's a great definition. It is a homogeneous mixture. It's a homogeneous mixture, and it is made solution is made of a solute plus a solvent. Now, what is the solute here? Solute can have several definitions. One of the definitions is the smaller amount of the solution, and the solvent is the larger, present in a larger amount in the solution. Now, another definition is solute is being dissolved, or not dissolved, let me use a different term here, absorbed by the solvent. And the solvent absorbs the solute. And of course, if you look at the more advanced books, they will define the unsaturated solution, saturated solution, the supersaturated solutions. These are different types of solutions. And in this textbook, they pretty much talk about the dilute solution versus concentrated solution. So this is, I'm going to examine this book on page 566 when they define these terms. But again, I'm used to definitions on saturated, saturated, and supersaturated. And I'm really quickly going to go into the definitions of these three terms, even though they're not mentioned in the book, but I still think it's important to understand the difference between the three. So the unsaturated solution will be the one that pretty much when you try to dissolve a certain amount of solute in the solvent, you will add as much as the solvent can absorb. Anything that cannot be absorbed now by the solvent will be precipitated out, and that will be forming now a saturated solution, where the going to be an equilibrium between the solid and the solute dissolved. But again, the amount that you added before you get to the saturated solution will be your unsaturated solution. So in other words, when you prepare unsaturated solutions, you're adding your solvent, you're mixing, you're adding, you're mixing. As long as the solute goes and being dissolved by the solvent, that is your unsaturated solution. Once you add a certain amount of the solute and you put it inside of the, solution now, and you stir it, and now it does not dissolve, that's when you form now a saturated solution. So the saturated solution, now you actually added more of the solute than the solvent is able to absorb. And the supersaturated solution is a little different now than the aforementioned solutions, because the way to prepare it is to first prepare a saturated solution where you're adding so much solute that the solvent now cannot absorb. So you're going to see that solid formed in the bottom of the flask. And then the next thing to do is you usually heat it up to a certain temperature, higher temperature, of course, than room temperature. And then you will stir it, and you will see that the solute now will go inside of the solvent. And then if you slowly cool down the solution now to room temperature, you will see that now whatever used to be a solid at the room temperature now went into the solvent, and that will be now a supersaturated solution because it has now amount of the solute that actually greater dissolved than in the saturated solution. So those definitions are very important, but your book omits these definitions. I am not going to hold you responsible for these definitions, but you should be aware of the terms such as unsaturated, saturated, and supersaturated solutions. Now, the 13.2 solubility part, 13.2 part of the chapter, solubility. Now, solubility talks generally about different types of solutes and how they dissolve based on the increase or decrease of temperature. And most of the solids with the increase, or liquids with the increase of the temperature, they dissolve, they have higher solubilities. However, for the gases, that's the opposite way. And your book does not really explain why, but it has to do now with once you increase the temperature, what you do is you're increasing also average kinetic energy of the molecules. And as the average kinetic energy of the molecules increase, they start moving faster in the solution, and that way they'll be able to break up the intermolecular interactions. And again, the problem here talking about the intermolecular interactions is that we'll never learn here the molecular geometry, electronegativity concepts, and without those concepts, it's very difficult for me to explain you guys the intermolecular forces. Now, but just be aware that the solids and liquids, with increase of the temperature, the solubility increase generally. Now, for the gases, it's the opposite effect. The gases' solubility will decrease as the temperature goes up. And you can actually see this, I guess, this in everyday life when if you have 2 cans of soda and you open up one of the cans, I mean, actually both cans you open up, and you take one of the cans into the refrigerator, and then the second one you leave outside at room temperature. So at the end of the day or next morning, you try to drink the beverage from the both, and you realize that the one that was left at room temperature is now flat, and the one that was left in the refrigerator still has the CO2, still has that, I guess, tingling sensation as you drink. So you still have that. It's not flat, it still has the gas inside. So that would be one of the, I guess, examples of solubility of the gases. Now, how does the pressure affect the solubility of the solutes in the solvent? Well, for the solids and liquids, it doesn't really matter, the pressure, but the gases will be affected, the solubility of the gases will be affected by the higher or lower pressure. The only caveat here is that the pressure of the gas will be let's say we take the same now example with the soda drink, and the way they make the CO2, carbon dioxide gas, to go into the solvent, into the liquid, into that mixture that the beverage is made of, is by putting about 5 atmospheric pressure on the surface of that mixture, and so now they make the gas by pressure to go inside of the liquid. But when you open up your beverage, there's no more 5 atmospheric pressure of CO2 over the surface of that liquid, and therefore the atmospheric pressure of CO2 is at least about, as far as I remember, 100 times less than 5 atmospheres, and therefore there's no more CO2 pressuring the surface of that liquid, and the CO2 now inside of the beverage start escaping. So again, the pressure does affect the solubility of the gases, but the pressure does not affect the solubility of the liquids and the solids. Oh, actually, I was wrong, and now on page 567, I can see that they do define the saturated, unsaturated, and supersaturated solutions. But I already, guys, explained you I gave you guys the definitions of each, and you should just look up on page 567 for the definitions of the saturated solutions, saturated, unsaturated, and supersaturated solutions. Okay, so again, my mistake here. I really did not see it here, but now as I go through the chapter, I actually see the definitions. Very good. That these definitions are very important, and I already guys defined those a few minutes ago. Now, there are aqueous solutions on page 568, and there are non-aqueous solutions. In the aqueous solutions, of course, the ones that the solvent is water, in which the solvent is water, and the non-aqueous solutions, you may have air as a solution, where you have a mixture of, it's a homogeneous mixture of nitrogen gas, oxygen gas, hydrogen gas, carbon monoxide, carbon dioxide gas, and all other different gases. And you can also have some alloy metals. These are also solutions because they're made up of different metals. And so in the next video, I'm going to cover, guys, 13.3. I have to break right now. This video is getting a little too long. So I'm going to have issues with uploading this video. So I'm going to cover 13.3, solution formation.